Hello, welcome to Digital Gravity Lab. I am Matthew Isler, and this is another one of my assignments for my PhD program in Computational Sciences and Engineering. So I'm going to jump right into this here. But the assignment for today is essentially regarding unlocking GPU performance through memory hierarchies. So in GPU programming, memory hierarchies play a critical role in performance optimization. So while global memory is large and necessary, but slow, shared memory can be fast but is limited, and we'll look at that. And it's also localized as well. So this assignment has asked me to write two versions of a simple CUDA kernel using Python via NUMBA is what I used. Another one that reads from global memory only, and one that uses shared memory to cache array segments per block. So I measure the throughput of both these versions and explain performance differences. And also, somewhat for fun, I also did a integrated CUDA C++ version as well and do comparison across that. So let's keep going. The actual task was to create a CUDA kernel that performs an operation like I equals I times 2. In my formulas, I actually used I plus I to double it, but it's basically the same thing. And one of them stores in global memory and one in shared memory. So let's jump into kind of how I set it up first. After I ran it a few times, I saw there's a big difference between small sizes and large sizes, so I basically run everything twice to look at the performance of small versus large. And so NUMBA kernel, the very simple under the CUDA grid here, this I plus I, and this whole CUDA system sets out the blocks of threads per block and things like that. Pretty straightforward, I guess, once you've done it a few times. And then you can see here the output. So at 10,000 calculations, it was taking 0.1 millisecond. I mean, that was a bit of a outlier, but it took 1 millisecond versus 0.03 for 100,000 at 0.03 for 500,000 and just 0.05 for 10 million. You can see the throughput drastically increase there for that. And if we go to larger sizes, and we scroll through this, pretty much the same thing. Just pulling those sets of larger files here. So starting 50,000, you see the throughput is very high, and then you see it kind of goes up a little bit more linearly in this, with the throughput staying the same. And in CUDA C++, so using this nvcc4jupyter library, or it allows me to actually directly compile C++ and write that here in Python. It's really cool. So smaller sizes. The speed is actually much faster. Starting at 0.01, going up just to 0.03, keeping very hot, increasing very quickly in that throughput, because going from 10,000 to a million here, or very large numbers here, right? To 100 million here is 0.03 seconds. So, yeah, big, not a huge time difference there. Now, if we jump here into these large ones, right, 0.0 or 0.5, starting basically 0.5, and then there's a huge spike here at the end as it actually drops. It seems when you get to 1 billion, the CUDA performance, CUDA C++ performance actually drops drastically. It was very interesting. I haven't looked into that too much more, going to billion and a half, etc. But at some point, I'll do that. And then plotting these. So these in the global memory here, you can see the NUMBA performance or the average runtime. It started out high overhead. I do a warm up and everything, but this would sometimes be there, sometimes not. It's kind of interesting. Every time I ran it, sometimes it wasn't super consistent. And then this CUDA C++ is, for low numbers, actually been very consistent. And you can see this nice performance graph for the throughput here. So that is global. And then here, looking into the shared memory. So we're going to start similar, same top here, but then just everything is written up quite a bit different in order to do shared memory. So there's a whole thread system here, syncing threads, bench work that's doing, and there we go. So then it takes it, stores it in the SMs, and runs that through. So let's just move forward. So smaller sizes, 0.04 down to 0.08 across here. Larger sizes, 0.6 going up to 10.5 milliseconds there for a billion, versus CUDA C, which you'll see here, 0.009. So shared memory is quite a bit faster. The bandwidth of shared memory is double, approximately double, so that's to be expected. 0.03 up there at the end, versus the larger sizes. You can see the throughput stay the same, and then at a billion it just crashes. So at 0.5, very linear increase. Throughput staying the same, but then it just takes 3 times longer for 30% more. Getting that billion there. And then graphing. So a lot more. The average runtime here for the smaller size. No big gap here at the top. It did spike a little bit and get into 50 million here for NUMBA, versus throughput. You can see the throughput kind of stayed the same. It did 5 times more processes, versus CUDA C. You can see the throughput just skyrockets. It doesn't speed up quite as much. For larger sizes, very consistent across the two. For shared memory between NUMBA and CUDA C++, and there is that drop there at a billion. I'm still looking at that, what that caused it, but yeah, this particular CUDA C++ just can't handle over a billion. But everything else pretty much stable. Okay, so let's look at combining these two graphs. So this here is the smaller ones. I just have small size and large size up here at the top, but all the numbers are here. But let's look at that graph. So you can see for smaller ones, that longest time is that global for NUMBA, then you get shared NUMBA, and then fairly little bit more consistency for global versus shared from CUDA C++. Very small run times, and then the throughput, which you can see just skyrockets with the CUDA C++ for smaller sizes. And here, the shared versus global runtime. So under 1 means shared is better. So shared is a lot better, particularly here for NUMBA. Shared was basically twice as fast for most of it. Less important for doing shared versus global for C++, but it still was faster for these lower numbers, lower totals. Okay, we're looking at the large sizes. There's 50 million to a billion. You can see here, very consistent average runtime for everything. That crash, of course, here at the end, a little bit higher for global, but shared was definitely a lot worse. And throughput, pretty consistent, again, except for that one. And then comparing the two, really didn't matter at all whether you shared or global until that right at the very end, in which case global was much better for over a billion. We'll look more about that in the future, but this is what I've got. Look forward to your comments, and if you want access to the code, let me know. But I will be posting it for my class here. Thank you very much. Talk to you later.